Hello everyone, this is Dr. Matt C. Howard and welcome to week 6 of your Business 255 class. And as you read or heard in either my email or the introduction video, this week we're going to cover correlation. This is quite different than what we've covered already in the course. I think it's, to me, a little bit easier, but we'll see. But it is different, so make sure that you listen to all of this video, you watch all of this lecture, because this will be a very important lecture moving forward throughout the class. Because a lot of the stuff we're going to cover in the next few weeks in this semester will be along the lines of correlation and will be different than what we covered before in the prior weeks. Okay, so far in the class we've discussed statistical methods that identify the differences between groups. Such as we've talked about things about the height difference between males and females. We will do a t-test. About the GPA differences of majors, we will do a one-way ANOVA if we had multiple groups for majors, and then something like the performance difference of multiple different training groups, which might be something like an ANOVA again if we had multiple training groups. So far in this class we've covered things to discuss the difference between groups. Now, moving on for the next few weeks, we're going to discuss statistical methods that identify the relationship between variables. So moving on for the next few weeks, we're going to be looking at things that identify the relationship between variables. So for instance, a question we could answer with these methods we're going to learn is, what is the relationship between height and weight? There's no groups there. You're not comparing groups. You're just trying to figure out the general relationship between two variables. Variable 1 being height and variable 2 being weight. Another example is the relationship between number of hours studied per week and GPA. Once again, we don't have any groups. Numbers of hours studied is a continuous variable. It could be anywhere from 0 to infinity, technically. And then we have GPA, which is also a continuous variable. That could be anywhere between 0 and, well, at South Alabama at least, 4.0. And then the third example is the relationship between number of years worked and supervisor-related performance. So numbers of years worked is again a continuous variable. It could be anything from 0 to infinity, technically. And then we could have supervisor-rated performance. So this might be on a scale from 1 to 100. And once again, there's no groups in that variable. So now we're going to talk about analyses that are used to determine the relationship between two variables. And these typically will not involve groups. Typically, these will not involve any groups. So we're switching gears, we're trying something different, and it should be fun. It should be exciting. We'll see. Okay. So for the purposes of this class, the main tests we're going to use to determine the relationship between variables are correlation and regression. So this week we're going to cover correlation, and then for the next several weeks we're going to cover regression. There's a whole lot to learn about regression, much less to learn about correlation. So correlation is a wonderful start to understand these concepts, and then we'll move into regression. So correlation is used to determine the linear relationship between two variables, linear being the word that is underlined there. So once again, we're still looking at the relationship between two variables, such as height and weight, and we're trying to figure out the linear relationship. So the linear relationship means that as one goes up, we also expect the other one to go up in a consistent amount. That if one goes up by 1 and the other one goes up by 2, we would expect that relationship to hold across the entire spectrum of those two variables. If one goes up by 1 and the other one goes up by 1, we again would expect that relationship to hold across the entire spectrum of those two variables. It's a linear relationship, and we'll come back to that concept. So some questions we can answer with a correlation are things like, what's the relationship between job satisfaction and job performance? We have two variables there, and we can determine the linear relationship between those two variables. Another one might be, what's the relationship between conscientiousness and self-esteem? If we measured those two using Likert surveys, so things like we talked about earlier in the semester, we have a scale from 1 to 7 for both of those. We could get people to respond on a scale from 1 to 7 for both of those, and then we can calculate the correlation between those two. And then the last example is, what is the relationship between self-esteem and weekly alcohol consumption? So we could give a Likert scale for self-esteem, and we could ask people, how much do you drink per week? We could calculate a correlation to see if there's a relationship between self-esteem and weekly alcohol consumption. So once again, we're just determining the linear relationship between these two variables. We're not comparing any groups here. So for correlation, we're not comparing any groups. So here's a visual representation of a correlation. So one way to think of a correlation is that straight line. That straight line identifies the linear relationship between the two variables. So when you're thinking of correlation, you should visualize it like this, where you have a scatter plot with one variable on the x-axis, in this example it's job satisfaction, and the other variable on the y-axis, in this example it's job performance. So in this example we plot each individual's observation. So all those little blue dots are a single observation for an individual. So as you can see near the bottom there, there's one person with a job satisfaction score of 5, and then a job performance score of 2. There's one person with a job satisfaction score of 3, and a job performance score of 2, and so on and so on. So we make a scatter plot to start, and then one way to think of the correlation is you draw the line that best fits that data. You draw the line of best fit. And that's what a correlation really does. It gives us an indicator of the relationship between those two variables by making the linear line of best fit, the linear relationship of best fit for that data. So that's how you can think of a correlation. So in this example, that line indicates that as job satisfaction goes up, on average job performance goes up too, because it's a positive line. That line goes up. So we would say that there's a positive correlation if we had this type of data. So here's another example. So in this example, we have self-esteem on the x-axis and job satisfaction on the y-axis. We plot each individual observation, which are those blue dots, and then we draw the line of best fit, and that represents the correlation. So as you can see in this example, as self-esteem goes up, as the self-esteem numbers get larger, job satisfaction actually goes down. Job satisfaction gets smaller. So in this example, we would say it's a negative correlation, because as self-esteem goes up, job satisfaction goes down, and vice versa. So we would say, therefore, it's a negative correlation. And then here's another example. We have on the x-axis conscientiousness. We have on the y-axis job performance. We plot each observation, and then we draw the line of best fit. And as you can see, this is a special instance where no matter what conscientiousness was, no matter what that number for conscientiousness was, job performance was always 1. It's a completely flat line. So what would we say about that? What type of correlation would that be? You might have guessed it. We would say that there's no relationship there. There is no relationship between the two, because no matter what conscientiousness is, no matter whether it's 1, 2, 3, 4, 5, 6, or 7, job performance is always 1. Job performance is always 1. So we would say there's no relationship between conscientiousness and job performance. Okay, so going back to that chart we go to every single week in this semester, we're no longer looking at the right side of this chart. We're no longer looking at the right side. We're now looking at the left side of this chart. So we're now looking at the relationship between variables. So no longer the difference between groups, but we're now looking at the relationship between variables. And how many variables are we studying? We're only looking at 2. At this point, we're only looking at 2 variables. So therefore, we're doing a correlation. So that's how we figure out when we would use a correlation, is we're looking at the relationship between variables, and we're studying only 2 variables, so therefore we're doing a correlation. Also, some other things to know is typically when we're talking about correlations, we might notate it as R. So if you ever see any type of statistical results that say R equals 0.30, it's probably referring to a correlation. So if you see something that says R equals point something something, it's probably talking about a correlation, because we often notate a correlation as R. And this is the test statistic. This is the test statistic from a correlation. So just like the t-test had a t-statistic, just like an ANOVA has the f-statistic, a correlation produces an R statistic. It also gives you a p-value, but the main test statistic is the R value. We call R squared the coefficient of determination. So you just literally take your correlation result and you square it, and that's how you get R squared. And the coefficient of determination is the percent of variance that's shared between the 2 variables. So it's the percent of variance that's shared between the 2 variables. So if 2 variables have a coefficient of determination of 0.05, we would say that they share 5% of their variance. And we're not going to get too much into that this semester. We're not going to discuss that too often this semester, but it is something you should be aware of. That is what the coefficient of determination is it's your correlation coefficient squared, and it represents the amount of variance that's shared between the 2 variables. And also related to that, if we're assuming that x predicts y, It can also be considered the percent of variance in one variable that's predicted by the other variable. So the amount of variance that's explained in that outcome variable. And we can only really do that if we're assuming that x predicts y. And as we'll talk more before, correlation does not equal causality, but we'll come back to that. Also, other information you should know about correlations and correlation coefficients is that correlations can range from -1 to 1. So if you ever calculate a correlation and you get a value of 3, you should automatically know, no, you're completely wrong, you're completely off base. A correlation should always be between -1 and 1. It should never be anything different than that. Also, negative values indicate a negative relationship and positive values indicate a positive relationship. So when we were looking at those charts before, if the line is going up, then that represents a positive value, that represents a positive relationship. On the other hand, if that line is going down, then that represents a negative value, and that represents a negative relationship. So keep that in mind. And also something else to know is values further away from 0 are stronger. That if your correlation is close to 0, that's a pretty weak correlation. So if you have a correlation of 0.1, maybe 0.05, that's a pretty weak correlation. But if you have a correlation that's something like 0.5, 0.6, or 0.7, that's pretty strong. We would consider that a strong correlation in the social sciences. Also, this is something else you should know that's a little bit tricky, is this holds true whether the numbers are positive or negative. So if you have a correlation that's negative 0.1, then that's still a pretty small relationship. But if you have a correlation that's negative 0.7, then we would also consider that a strong relationship. That when you're considering the strength of a correlation, it doesn't matter if it's positive or negative, we're just looking at the distance away from 0. So once again, when you're talking about correlations, we're just thinking about the distance away from 0 regarding their strength. So if it's a negative 0.7, that's just as strong as a positive 0.7 when you're talking about correlation. So with that in mind, here's a little quick pop-up quiz for you. We're going to go through some number pairings, and you can tell me which of these numbers are stronger, or which of these correlations are stronger. So to start, is 0.1 or 0.3 a stronger correlation? As you hopefully guessed, 0.3 is a stronger correlation than 0.1, because 0.3 is further away from 0. The next one is 0.20 or 0.70. As you probably guessed, 0.7 is stronger because 0.7 is further away from 0 than 0.2. Okay, how about this one? Negative 0.3 or negative 0.1? So this one's a little bit trickier. The answer is actually negative 0.3 because negative 0.3 is further away from 0 than negative 0.1. So therefore, negative 0.3 would be stronger. The next one is negative 0.3 or 0.5. So in this example, 0.5 would be stronger because 0.5 is further away from 0 than negative 0.3. If we're to think about these, you could also think about it as taking the absolute value of those. The absolute value of negative 0.3 would be 0.3. The absolute value of 0.5 would be 0.5. So because the absolute value is stronger when you have 0.5, the answer is 0.5. That is the stronger correlation. Here's another one, negative 0.5 or 0.3. The answer is negative 0.5. Negative 0.5 is a stronger correlation because negative 0.5 is further away from 0 than 0.3. If you were to take the absolute value of negative 0.5, that would be 0.5, and that is stronger than 0.3. So therefore, negative 0.5 is a stronger correlation. And then here's the last one, negative 0.15 or positive 0.15. This one's a trick question. They have the exact same strength. That even though one is negative and one is positive, they both are an equal distance away from 0, so therefore they have the same strength. Okay, so when performing a correlation analysis, our null and alternative hypotheses are usually, our null is usually no relationship exists between these two variables. And then our hypothesis, or the alternative hypothesis, is typically a relationship exists between these two variables. So whenever we perform a correlation, we'll get our R statistic, we'll get our p-value, and hopefully our p-value is going to be less than 0.05, so we could therefore reject that null hypothesis. We therefore could reject that no relationship exists, and we'd be able to claim or support our hypothesis that a relationship does exist. So we're trying to hopefully show that some type of relationship does exist whenever we're performing a correlation analysis. So we perform a correlation analysis to determine whether we can reject the null, and once again we're still going to use p-values to do this. And how do we perform a correlation analysis? Like everything else in this class, we're going to use Excel. But before doing so, let's make two quick notes about correlations. Two very quick notes. So first off, a correlation assumes a linear relationship. And as I mentioned before, one way to think about this is to create a scatter plot and then draw the straight line that best describes this data. So here's more visual representations. So if you have a positive correlation, that straight line that fits that data is going to go in a positive direction. If you have a negative correlation, the straight line that describes that data will go in a negative direction. And then if you have no correlation, you're just going to have a scatter plot that looks something like that. And I wish this example did draw a line. The line would be a straight flat line. It would be a flat horizontal line for that cluster of data for no correlation. So that's one way to think about a correlation. Is first off, it does indicate the linear relationship between two variables, and you can think of it as drawing a scatter plot. So can you think of any concerns with that? Can you think of any problems with that? So some of y'all might have guessed that sometimes your data can look very, 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 very different, but then give you the same correlation, but then give you the same line of best fit. So let's look at 4 examples in the following slide. So the top left one, it's what you would pretty much expect with normal data, data you would use for a correlation. At the top left one, you have a scatter plot. You see there's a general increase in x and a general increase in y, and therefore there is a positive relationship between those two. So that's what typical data will look like. But let's look at the second example, which is the top right. So as you can see, that data is clearly not linear. That data is clearly not linear. It's best described by a curve. A curve would best describe the data in the top right. However, if you were to run a correlation on that data, it would give you a pretty strong result. It might be significant, and it will give you actually the same result as the top left data. And as you can see, the line is the same slope. The line looks the same. So even though those two pieces of data look very, very, very different, the correlation would be the same. The same is true with the bottom left graph. As on this graph, typically when x goes up, y goes up, but you see there's one outlier. There's one observation that's very different than the others. So therefore that causes the correlation to be increased. That causes that line to not really fit that data as well. That one outlier is throwing off your line of best fit. So it's causing it to not only not represent your data that well, but it's also causing it to give the same result as the prior two that we looked at. So once again, even though this data looks very, very, very different, it actually gives you the same result. And in this example, the result could be misleading because you have that one outlier. And the same is true with the very last one, the bottom right. So in this example, we have for most of our data, no relationship between x and y. For most of our data, it doesn't matter what y is, x is always 8. But then we have that one super weird outlier that x was 18 and y was 12. And because we have that super weird outlier, our correlation is going to actually give us a pretty strong result. It's not going to be a 0 like it should be. It's going to give us a pretty strong result, and it's going to be the same as the other 3. So once again, although this data looks very different than the other 3, it gives us the same results. So the lesson you should learn from that is other analyses can better analyze nonlinear data. And this is something to keep in mind as you analyze data throughout the semester and during your professional career. So one thing you should do whenever you're thinking that you need to run a correlation or a regression or any analysis that looks at the relationship between two variables is you should go ahead and make a scatter plot. Go ahead and make a scatter plot and try to get a general inference of the shape of your data. So try to get a general understanding of what does your data look like? What is the shape of your data? And if it looks linear, then good. Go for it. Calculate that correlation. Do that regression. But if your data is not linear, you need to perform a different analysis, because your results could be very misleading if you have nonlinear data and you perform a linear analysis. So just keep that in mind. We're not going to harp on that too much this semester, but it is something you should be aware of. Also, something else you should know is correlation is not equal causality. So just because there's a correlation between two variables does not mean that one causes the other. So for example, this is something that always happens, or stats classes always talk about, is in many data sets, this relationship is statistically significant. There is a statistically significant correlation between ice cream sales and murder rates. That in geographic areas, whenever ice cream sales go up, typically murder rate goes up too. So does that mean that ice cream sales causes murder rate? Does that mean that people go out, they buy ice creams, they go crazy, and they kill people? Hopefully not, and I think it's safe to say probably not. So just because there's a correlation between these two does not mean that there's a causal effect. Actually, what most people assume, or what most researchers assume, is that ice cream sales and murder rate both have a common predictor. So there's some type of third variable that predicts both, that makes them seem like they're related, that makes them seem like that there's something going on there, and it does cause them to have a correlation, but it's only because there's a third variable that predicts both of them. Can you guess what that third variable is? A lot of people assume it's actually temperature. That when summer starts, when things get hotter, people tend to buy more ice cream sales, people buy more ice cream, but there's also a higher murder rate. People get more anxious when it's hotter, and people are out more. When it's cold, people stay inside, they don't do as many, dangerous activities. But once it gets hot, people are more active, they're more likely to get stressed, and therefore murder rate goes up. But also when it's hot, people buy ice cream. So that makes it seem like that makes it actually to have a correlation between the two, because when one goes up, also the other goes up, but there's not necessarily a causal effect. There's not a causal effect between these two. There's a third variable that instead explains that relationship. Just remember that in the future, that correlation is not equal causality. And there's other examples that happen all the time that seem like they make sense, that now there's some doubt whether one actually causes the other. So another one is job satisfaction and job performance. So for a long time in business research, everyone just assumed that if an employee is satisfied with their job, they're going to be a higher performer. That job satisfaction causes job performance, and no matter what, you almost always find a significant correlation between these two. However, more recent research is starting to hypothesize that it's maybe job performance that predicts job satisfaction. That sometimes it's not necessarily that you're happy with your job, so therefore you work harder. It's instead that people tend to work hard by their natural nature. People by default tend to be hard workers. And then if you perform well from your effort, you then become satisfied with your job. You then start to like your job. So it's instead not that job satisfaction predicts job performance, but instead it's job performance predicts job satisfaction. There's still some questions about that, but just keep that in mind, that it might not be that one predicts the other. It's maybe not that X predicts Y. It could instead be that Y predicts X. And that could always happen when you find a correlation. And then here's another website. Go ahead, check that out. You type it into your browser, and it's a collection of significant correlations. Some of these are incredibly strong. They're correlations of 0.99, for instance. So incredibly strong correlations that are complete bogus relationships. They make no sense. This website is a collection of things that should never be related, but they find a significant correlation. So sometimes you just find random weird correlations that are significant that just make no sense. So just because they're significant doesn't necessarily mean that they're causally related. Okay, so with those things noted, let's go ahead and calculate some correlations in Excel. So this is going to be the same as in your guide. This is going to be something you can watch in this video and then follow along on the guide that I provide in my email. So in this data set, we're going to have three variables. In this example, we're going to have job satisfaction, self-efficacy, and job performance. So those are three variables, and we're going to have 29 participants. So 29 people completed a survey on all three of those variables of job satisfaction, self-efficacy, and job performance. And let's say we wanted to calculate correlations between these three variables. So we want to calculate a correlation between job satisfaction and self-efficacy, job satisfaction and job performance, and self-efficacy and job performance. So we can go ahead and calculate a correlation between these three variables. So first off, like everything else, we would go to the Data tab and we would click on Data Analysis. Our window would pop up, and as you probably guessed, we would click on Correlation. So we'd click on Correlation and push OK. So the first thing we should do is, sorry, I clicked too fast. So the first thing we should do is on this data, or on this window that pops up, like usual, we need to tell it where our data is located. We need to tell it our input range. So we click on that highlighted button, and then we highlight all of our data. And as you'll see in this slide, not only did I highlight my data, but I also highlighted the labels. And this is very important. This is very important that you do this. Make sure you not only highlight your data, but you also highlight your labels. If you don't do this, your results will get very confusing, so make sure you highlight your labels. And then you click on that other highlighted button that I have highlighted in the slide. Next, before you push OK, you need to tell it you included the labels. So we're going to click that little checkbox for labels and first row. So go ahead and click that little checkbox for labels and first row, and then push OK. So your results should look like this, and as you'll see, we do have the labels included. So if you do not have the labels, you either forgot to highlight the labels, or you forgot to click on labels in first row. So if your data does not look like this, or if your results do not look like this, go ahead and calculate your results again, because you need those labels. But hopefully you did get these results, so let's look at how to read them. So when you're looking at a correlation table, which is what this is called, the easiest way to read it is you try to find where a particular column intersects with a particular row. So as you'll see, that first column is job satisfaction. The very first column is job satisfaction. So this column will include the correlations of job satisfaction. So if we move down this column, we see the first one is a 1 between job satisfaction and job satisfaction. We're just going to ignore that. That doesn't really mean anything. So just ignore that first row in that first column. The next one, we see the number is 0.16. The number is 0.16. And this is the correlation between job satisfaction and self-efficacy. So this is the correlation between job satisfaction and self-efficacy, which is 0.16. And we get that because that's where the column of job satisfaction intersects with the row of self-efficacy. So based on that, we would say that the correlation between job satisfaction and self-efficacy is 0.16. And it doesn't matter what order you say that in, it doesn't matter what order you put that in, because correlations don't have a real order. It's just a correlation between two variables. So therefore, if you say it's the correlation between self-efficacy and job satisfaction, that means the same thing as the correlation between job satisfaction and self-efficacy. Either way, it's 0.16. Okay, let's move on to the next one. So the next one is, you see in the job satisfaction column, there is a number of 0.509, so that would round up to 0.51. So we would say that job satisfaction in that column, and the row is job performance, have a correlation of 0.51. So we would say the correlation between job satisfaction and job performance is 0.51, because that's where the job satisfaction column intersects with the job performance row with a number of 0.51. And the very last one, let's move over to the next column where there's self-efficacy. So we see that the first number there is a 1, we ignore that one, move on to the next one, and we see that's 0.2059, which rounds up to 0.21. So we'll just say that that is 0.21. So since that's in the self-efficacy column, and that's in the job performance row, we say that there is a correlation of 0.21 between self-efficacy and job performance, because that's where the self-efficacy column and the job performance row intersect. So therefore, there's a correlation of 0.21 between self-efficacy and job performance. So from these results, we can determine that job satisfaction and self-efficacy have a correlation of 0.16, job satisfaction and job performance have a correlation of 0.51, and self-efficacy and job performance have a correlation of 0.21. So these would be your R statistics. These would be your test statistics. You would need to report these, and I will ask you for these on the homework. But which of these are statistically significant? As of right now, you cannot tell. Excel does not have an easy way to determine correlation p-values. And that's really weird. I have no idea why Excel does that. It makes no sense. But for some reason, Excel does not provide correlation p-values. We could learn the formula to figure this out, but it's a pretty complex formula. And instead, we're going to use a free website to do this for us. So multiple ways to find free websites. You could just Google search correlation p-value calculator, and you'll find a dozen, maybe 24 websites that will do this calculation for you. That will give you a p-value based on your correlation. Also in this slide, I provide two of my favorite. I If I forgot to, I will intend to send these out in my email to the class, but if I forgot to, please send me an email and I'll go ahead and send that out. I'll send these 2 links out to the class so you don't have to type those back in. But these are 2 of my favorite websites, so take a look at those first to figure out how to calculate a p-value from your correlation. So to use these calculators, we need the correlation coefficient, also known as the test statistic or the R value, and we need the sample size. So in our examples we just now did, if you look at our data set, we had a total of 30 rows, but that included the labels. So we take out the row that had the labels. So we had 30 rows, but that included the labels. Since we need to take out that row with the labels, that gives us a sample size of 29. So for our analyses we just now did, we had a sample size of 29, and we already calculated all of those R statistics, all those correlation coefficients, also known as test statistics. So we just need to go ahead and put those numbers into the calculator. So here's an example what the calculator looks like. I think this is the second one on the 2 that I provided. I might be wrong about that, but check out both of them. Do the one you're more comfortable with. But here's a visual representation of what they look like. So in these calculators, you typically will first enter your R score. So you just enter your correlation coefficient. So this is the number that you calculated. So in this example, I'm testing a correlation of 0.16. And then you enter your sample size where it says N. N as a way to represent sample size. So in this example, we had a sample size of 29. So we had an R score of 0.16 that we enter. We had a correlation of 0.16 that we enter there. We had a sample size of 0.29 that we enter for N. And then it asks for our significance level. We're just going to put that as 0.05 because we're usually interested in alpha and a significance level of 0.05. So we put in 0.16. We put in 29 for our sample size. We tell it a significant level of 0.05, and then we click on calculate. And it will give us the result right there. So based on this input, our p-value was 0.41, rounded up. So our p-value is 0.41. And as you can see, our p-value calculator directly tells us this is not significant at the p less than 0.05 level, because a p-value of 0.41 is greater than 0.05. So therefore, this result is not significant because the p-value is greater than 0.05. So go ahead and try to do the other ones on your own that we just calculated. And pause the video, go ahead, calculate it, and then we'll look at the results. Okay, so if you went ahead and did it on your own, the p-values for job satisfaction and self-efficacy was 0.41. The p-value for job satisfaction and job performance was 0.004, and the p-value for self-efficacy and job performance was 0.27. So what can we say about these results? Well, first off, we can say there was not a significant relationship between job satisfaction and self-efficacy, because the p-value was greater than 0.05. We could also say there was a significant relationship between job satisfaction and job performance, because the p-value was less than 0.05. So therefore it was a significant relationship because the p-value was 0.004, and that is less than 0.05. So there was a significant relationship between job satisfaction and job performance. And then the very last one, we would say that there is not a significant relationship between self-efficacy and job performance, because the p-value is 0.27, which is greater than 0.05. So there is not a significant relationship between self-efficacy and job performance. So that's all you really need to know about correlations. We learned how to calculate the correlation coefficient, we learned how to calculate the p-values, and based on that you can determine whether your results are statistically significant. So that's all I have for this week. This is a very short lecture this week. So send me an email if you have any questions, but don't forget to watch the introductory video to this week if you haven't already, and don't forget to do your homework. So that's all I got for you in this video. Thank you for listening, and I will talk to you next week.